So let's talk about partial derivatives. Basically, a partial derivative is a derivative in a certain direction. So let's look at a little bit of Cal 1 first. If you have some graph in Cal 1 and you want to take the derivative, let's say at A, you go up to the graph, take the derivative, and that's going to be the tangent line there, the slope of the tangent line. So you had f prime at A was the slope of the tangent line. You could go one of two different ways to get to A, left or right. However, whenever you have a surface, let's say in 3 space, so let's say it's a kind of upside down paraboloid, whenever you take the derivative at a point, let's say at this point, it's this point right here, when you go up to the graph, the derivative is not only in one direction, it's in many directions. There's slopes in many directions. So the slope of a of a curve is one thing, but the slope of a surface is another because there's many different ways you can go and the slope is different. So one way to look at this is to cut the surface with, so I have an upside down paraboloid here, is to cut it with a plane. So I'm going to cut it with a plane. And then you look at the curve of intersection of the plane with the surface. And then at that point A, or x comma y in this case, you go up to the curve, you have a tangent line there, and then the partial derivative will be the slope of the tangent line there. So you can go in many different directions, right? So you can go in many different directions, and if you notice, the tangent line will change accordingly, and so the slope will change. So the partial derivative will be the slope in a certain direction. So the partial derivative when x is constant, see how x is constant here? The partial derivative when x is constant is called the partial with respect to y, because y is one varying. The partial derivative when y is constant, so let me turn this around. So now y is constant. That'll be the partial derivative with respect to x because x is changing as we go. And so these two partial derivatives are usually not the same. I mean, in this case, they might be because of the symmetry of this paraboloid, but they don't have to be the same in general. So one way you can, there's another diagram that the book has that illustrates this pretty well right here. So you just cut the surface with this plane here, and then you have a curve that is the resulting curve of that. It's right here. And then you, at your little point, whatever that point is, you look at the slope of a tangent line there, the slope of your tangent line there. All right, so in this case, this one right here, that is where x is changing. So if we assume this is x and this is y, so x is changing. So if your function is z equals f of x, y, your partial derivative with respect to x, so partial derivative would, let me write it out, the partial derivative with respect to x, is written f sub x at x comma y, f sub x, or you can write it as z sub x. So this means that y is constant, y is held constant for that value, and x is changing. So x varies, it's the variable. So the reason x is changing in this case is because as you go, x is changing like that. All right. So, all right. So then if y is changing, oh, they screwed this up. I'm going to call that y and this x. This is y and this is x. That's normally where they're at. Anyway, so it doesn't. I mean, it doesn't really matter. All right. So in this case, y is changing, and x is held constant. And so in this case, your partial derivative would be f sub y of xy, f sub y. All right. So question is, well, how do you do that? Well, there's a limit process to all of this, which I'll let you look at in the book right here. this the limit process. So recall from Cal 1, the derivative with respect to x is limit as h goes to 0 of f of x plus h minus f of x divided by h. Well, you have a little bit of that here. So maybe at the end of this video I'll explain that. Let's just do a partial derivative. And then I want to go back to this and talk about an actual application of it. First of all, you have some notation. So f sub x xy, f sub x of xy is also written f sub x, just that, and then this guy right here, partial of f. It's like a curly d, partial f with respect to x, curly d, and you can write it like this. This is equivalent to when you had the derivative with respect to x of f of x, like that. So it's written similar to that. Z is f of x, so z is f of xy. So you can say the partial of z with respect to x, or you can write f sub x like that. So either one works. This is kind of like when you had in Cal 1, you might have had something like y equals f of x, and then the derivative could be written three different ways. F prime of x could be written dy dx, and then you could also be written d dx of y, like that. So there's just other notations. These two you'll see later on in other theory. We don't need to worry about it now. F1 sub F2, F sub 1, F sub 2, those are really more for whenever you have three or more variables involved. So let's do one of these examples here. It's a good one. This one's in the book, so I'll let you look at that. I'm going to pick one out of the example, out of the exercises, and do that. All right, so what I've done here is I've gotten a function of my own. I just created it, and I graphed it using academo.com. Let's find that. It's academo.org. I just Google searched plot surface, and it's really cool because you can spin this thing around. Anyway, we're going to take the partial derivative. So here's my function. I'm going to do partial with respect to x. So I keep the y constant, and I just let the x vary. So the x is going to be the variable for now. So if y is a constant, it just stays there unaffected by the derivative. So that's 2x squared y squared. So it's going to be 4x y squared. Y is a constant, so it stays. And then on the second one, it's going to be plus 10xy. Now I'm going to take the derivative with respect to y. Now the x is constant, so that'll be 4x squared y plus 5x squared. X is a constant, so in this case, so if this here is a constant, it's just the derivative with respect to y is just the constant. All right, so that's these two. So notice they're not the same. They don't have to be. And so wherever I'm at on this curve, so this is x and this is y. It's the axes are kind of odd, but this is what we got. X is still going in this direction, and y is still going in that direction. That's all. So if I'm at the point, for example, 1, 2, so over 1, up 2 in the y direction, that's here. 0, 0 is this right here. So I'm going to go over 1 in the x direction and up 2 in the y direction. All right, so that is right there. So if I go up to the graph, I have a derivative in the x direction. I mean, in the strict y direction, because this is y, so I'm in the strict y direction. And then I have a derivative in the x direction, strict x direction, like this, x direction. So it kind of looks like the derivative with respect to y is going to be smaller than the derivative with respect to x. Let me pull in the plot of this thing, and we'll spin it around, and I'll show you. So we have 0, 0 here, and then if I spin it around, if we're at the point over 1 up 2, it's kind of right there. over 1 up 2. No, it's not allowing me to do it. There it is. It's there on the graph itself. Then over 1 up 2, it's kind of like right there. If you look, going in the x direction is pretty steep, but going in the y direction over there, it's not as steep going this way. All right, so let's go ahead and plug those numbers in and see what happens. So now I'm going to plug in the value 1 comma 2 into both 1 comma 2. And this is written as follows: f sub x at 1 comma 2. So when I plug in 1 in for x and 2 in for y, 1 in for x and 2 in for y, I think I'm going to get 16 plus 2 in for y, 20. So it's 36. So this is equal to 36. And then let's do the same thing for this one here. When I plug, this is going to f sub y at 1 comma 2. This is going to give me, so I plug in 1, plug in 2, I'm going to get 8 plus plug in 1, 5. So it's 13. So in the y direction, it's smaller than in the x direction, and that's exactly what we what we figured out. We pull this back. Yeah, so in the wider, in the strict x direction, at 1, 2, which was right here, it was pretty steep, but in the y direction there, it's not really steep at all. It's somewhat, but not as much. So that's what we got. So let's do another one of these. I want to do this one here, sine x. So this one here is sine x minus sine y. All right, so I'm going to copy and paste this and move it over. All right, so here we are. So instead of using Wolfram Alpha, which gives me this graph like this, I'm going to use Academo again, which gives me this nicer graph that I can spin around. Wolfram Alpha, you have to pay for it to spin it around, and I just wanted to find something that you guys could use. It's kind of a pain for me to have to pay for it too. Anyway, so here we are. It's sine x minus sine y. So I'm going to take the derivative with respect to x, and I get cosine x. And then this goes away. This part goes away because that's just a constant, right? And then f sub y will be the sine x is gone because that's just a constant. And so it's just negative cosine of y, right? You can put parentheses here if you want, doesn't matter. All right, so what I want to do now is I want to pick a point to evaluate, and let's see what's going on. It kind of looks like a 4, 4. So this is the y direction, this is the x direction. Kind of looks like at 4, 4, it's interesting. So let's plug those in. These are 4 radians. Might be easier if we plug in pi comma pi, but I want to do, let's do pi pi. I think that must be pi comma pi right there. So if we do f sub x at pi comma pi, which is 3 comma 3 basically, we get f sub x, that's this one. There's no y to plug in, just the x, right? There's no y to plug in, so we just plug that in, and that's negative 1. And then f sub y at pi pi is this negative, we're going to look at this one now, negative 1, which is just positive 1. So it's positive 1. All right. So in the x direction, in the strict x direction, it's negative, and in the strict y direction, it's positive. So what I'm going to do is I'm going to bring over the graph that we can spin around, and let's see if that looks like it's the case. All right, so here we are. So we're at 3, 3. Let's see if I can get there. At 3, 3, it's about, let's see, 3 up 3, it's about right here. And it's kind of hard to tell, but in the strict y direction, it's going up. There we go. That's 3.6. Let me go back some more. Okay, I think I'm gonna have to settle on 3.6 comma 3.6, which is about all it's giving me. I tell you what, let's do 4, 4. That'll be good. Let's see, 4, 4, where are we at? 4, 4. That's good enough. All right. So if you notice, going keeps moving. Um, Going in the strict x direction, if you look at where 4, 4 is, let's just say it's there. In the strict x direction, it's going down, and in the y direction, it's going up. So let me spin this around. See, if you're going in the strict x direction right around 4, 4, it's going down, and in the y direction, I can't really tell. Yeah, it's going up, and that's what we found. In fact, I went ahead and did it at 4. Now this is 4 radians, so when you do 4 radians, uh, that's a little more than pi. Well, it's more than pi, but so you get negative for x and positive for y. Anyway, so that's how you do it. All right, so let's move on. Once again, that website is academo.org, and I really recommend you do it. You play around with it. If you need help with it, just email me. All right, so this is what the book has, and they talk about that. So I want to talk about if a function is implicitly defined. So implicit differentiation, remember from Cal 1, so implicit differentiation, you had things like this. You had x squared y plus yx minus sine of y equals y squared, things like this. And you had to find dy dx. But the problem is you can't find what y is. You can't solve for y here. So this is where when you take the derivative, you take the derivative with respect to, let me make this a little easier. I'll do that. Let me do this, x squared plus y. There we go. That'll be a little easier to work with. So 2x and then plus, make this a 3y. And then 3 dy dx. Everywhere you see a y, you're going to put a dy dx. I don't like saying it like that. If you need to go back and learn why you do that, I have a video on that that I can send you. Now we take the derivative of this. Derivative sign is cosine of y, and then we write dy dx. And then on the other side, we have 2y and then dy dx. And then you solve for dy dx and moves things around and you get an answer. For this material now, with partial derivatives, you may have something like x squared plus y squared plus xy z equals, let's say, z cubed. And it's kind of hard to, well, we'll make it even harder. How about just natural log of z? Now you really can't solve for z. So to find z sub x, so it's implied that z is a function of x and y. You just can't solve for it. Just like up here, it was implied that y is some function of x, but you just can't solve for it in this. It's hard. It's almost impossible to solve for y in that. In fact, it pretty much is. So you can't solve for y in terms of x, and same thing here, you can't solve for z in terms of x and y. So what you do is you still want to find the partial of z with respect to x and want to find the partial of z with respect to y. Keep in mind, these are just another way of writing f sub x and f sub y, all right? Because z is f of x, y. All right, so what you do is you do the same thing that you did in Cal 1. So I'm going to take the derivative with respect to x. So I'm going to find partial z with respect to x first. Let's see, partial x. All right, so I'm going to take the derivative with respect to x in my equation. Let me go ahead and write it just below it. So it's going to be 2x. Y is a constant, so that's going to be 0. Plus, all right, this is a product rule. Derivative with respect to x would be y times z plus, and now the derivative with respect to z will be x, y, because these are just constants with respect to z, and then partial of z with respect to x equals, right? So the derivative of this piece is 1 times the partial of z with respect to x. So that's why I wrote that here, all right? If there was a 2 in front of that z, it would be 2 times that. And then natural log of z is just the partial, remember the natural log of x, when you take the derivative, it's, whenever you take the derivative of u, it's u prime over u. That's from Cal 1. So this will be the partial of z with respect to x over z, like that. I don't know what the partial of z with respect to x is, so I have to write it down. And now we just solve for that. And it's kind of like writing z prime over z, like we wrote u prime over u before. And now you just solve for partial z with respect to x. So I'm going to multiply everything by z, so z times 2x plus yz plus xy partial of z with respect to x equals partial of z with respect to x, and then you multiply this through. Let me I'll do the math and pause the video. Okay, so I did all the work here, so let me show you what I just did. So let me draw a line from where I was before. So that's where we were. So now I multiplied everything by z. So that's right here. Multiplied everything by z, and I put z on the side, right? Okay, now I multiplied z through. So we multiply z all the way through everywhere, and we got what the next line is. You can pause the video at any time you need to. And then, so now I got this line, and so let's cross that out. And now, well, now we move the dz dx on the other side, that term, and then I factored it out here, and then I divided, and I got my answer. And so this is the partial of z with respect to x. That's what this is. And then you do the same thing for y. So I'll start you out on the one for y. So what we've got is x squared plus y squared plus xy z equals natural log of z. Actually, it's going to be the same thing because x and y are symmetric. So it's really not that interesting. So let's look at a different one that might be a little harder. Yeah, so let's look at this one here. Yeah, okay, I can remember that one. It's x cubed plus y cubed plus z cubed plus 6xyz equals 1. So derivative with respect to x. So we're going to do 3x squared plus, this is now 0. All right, so 3z squared partial of z with respect to x. I'm going to write it like that this time. Plus product rule. Derivative with respect to x is 6yz, because these two are constants with respect to x. Plus partial of z with respect to x will be 6y, and then partial of z with respect to x, and then this equals 0, derivative constant 0, and now you just solve for z sub x, dot, 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 factor it out and do all the business there like you did in Cal 1. All right, so that's that. Higher derivatives now. So you have second derivatives and mixed derivatives this time. So if you take the derivative with respect to x first, and then you take it again, we're going to write it a certain way. So if you have f of xy, then the first partial derivative of x is written f sub x. Then the second one is f sub x x. So if you have f of xy equals, let's say, 4x cubed minus 6y to the fourth, let's say f sub x would be 12x squared. F sub x, let's put an x in there, minus 6y to the fourth. Yeah, and then f sub xx, now you take the derivative of this with respect to x, so it's 24x. This is gone because that's a constant now. All right, now we can do a mixed partial though. Take the derivative of x, and now then take the derivative with respect to y. So I'm going to take whatever I have in this line right there and take the derivative with respect to y. So this would be negative 24y cubed. You can do the same thing for y, all right? So I'm going to take my function, I'm going to take the derivative with respect to y, this function here, and I get, first term drops out, I get negative 24 y cubed x, and then derivatives back to y again, I get negative 72 y squared x. X is just a constant. And now I'm going to take this one here, f sub y sub x. All this is a constant with respect to x. So it's just going to be negative 24 y cubed. And these are the mixed partials. Now, if you notice, these two are the same. And that brings up what's called Clairaut's theorem. Clairaut, this is in a book, Clairaut's theorem. It says if the mixed partials are continuous, then they are equal. So if f sub x y, if f sub x y and f sub y x are continuous, then they're equal. Then they're equal. And so we like functions that work this way. And f sub xy is equal to f sub yx. These are both continuous, and so they're equal. All right, that's Clairaut's theorem. So it's kind of nice to prove that, actually. All right, so let's do an example, another one that might be a little harder, like this one. Let me do this one first. Natural log of x plus 2y. Right, so we have z equals f of xy, equals natural log of x plus 2y. So remember, the natural log of u, whenever you take the derivative of it, it's u prime over u. Remember, natural log of x, when you take the derivative of it, this was 1 over x. The only reason that was a 1 there was because the derivative of x is just 1. So but if this is a function inside, you're using a chain rule to take care of it. And so when you do this one here, when you take the derivative with respect to x, it'll be z sub x, or f sub x if you want, over z. So z sub x will be 1, and then over z is x plus 2y. And then to do the partial with respect to y, it's z sub y over z, z prime over z basically. Z sub y is 2, and then over z is x plus 2y. All right, so these are the two answers for that. It does get a little harder whenever you do stuff like this one here, but I'll let you work those out, and maybe I'll do a different video on those. All right, so that's it. That's partial derivatives, good introduction to them.